In this video, we're going to learn about a mixed factorial analysis of variance, or mixed factorial ANOVA for short. We'll begin with an overview of mixed factorial ANOVA, then we'll shift gears and talk about the statistical assumptions of a mixed factorial ANOVA, and then finish up by talking about statistical significance, effect size, and practical significance in the context of a mixed factorial ANOVA. So let's begin with that overview. So, like t-tests, the analysis of variance or ANOVA is part of a family of analyses aimed at comparing means. Now, specifically, the ANOVA is really designed to compare 3 or more means, although you can use it to compare 2 means. However, if you have just 2 means that you wish to compare, often it's going to be easier to implement and easier to interpret if you use some type of t-test, such as an independent samples t-test or paired samples t-test, depending on the nature of your data and your predictor variable. Now, there are different types of analysis of variance or ANOVA. There's the one-way ANOVA that has just a single factor or predictor variable. There's the repeated measures ANOVA, which means that you have at least one variable in your model, your predictor variable in your model specifically, that's within subjects. You have a factorial ANOVA, which is where you have an ANOVA where there are 2 or more predictor variables, or in other words, 2 or more factors. And then lastly, the focus of today, of course, is going to be on the mixed factorial ANOVA, and we'll dive into some of the details and what distinguishes it from some of the other ANOVA that I've mentioned previously. So a mixed factorial ANOVA includes at least one within subjects predictor variable and at least one between subjects predictor variable. So you might be asking yourself, what's a within subjects predictor variable? Well, a within subjects predictor variable is one in which each person or case in our data is exposed to all levels of that particular predictor variable. Sometimes this is called repeated measures. So for example, if we give the same group of people and every single person in that sample participates in multiple measurement or waves of assessment in a given test, for example, that would be an example of a within subjects variable. Now, a between subjects predictor variable or a between subjects variable in general, this is going to be one where each person or case in our sample or a data set is exposed to only one level of that variable. Sometimes this is referred to as independent samples predictor variable. Now, along those lines, to review, an independent samples t-test involves a between subjects predictor variable, whereas a paired samples t-test involves a within subjects predictor variable. And so in some way, in a very simple sense, you can think of a mixed factorial ANOVA as combining an independent samples t-test with a paired samples t-test because we have both a within subjects variable as well as a between subjects variable. Now, if we have a mixed factorial ANOVA, or really any factorial ANOVA for that matter, and that mixed factorial ANOVA has 2 predictor variables, we can also refer to it as a two-way ANOVA. And if it were to have 3 predictor variables, we could refer to it as a 3-way ANOVA, and so on and so forth. Now, regarding this name or this term mixed factorial, the word factorial indicates that there are 2 or more factors in the model, where factors refer to categorical predictor variables in our model. And when I use the term categorical, I'm meaning that the variable has a nominal or ordinal measurement scale. Now, in the term mixed factorial, the word mixed indicates that there's a mix of between subjects and within subjects factors or predictor variables. Sometimes you'll hear a mixed factorial ANOVA referred to as simply a mixed ANOVA. Now, a mixed factorial ANOVA is going to require the following 3 things. At least one of the predictor variables needs to be categorical in nature, and at least one of the predictor variables needs to be a repeated measures or a within subjects variable. So that first categorical variable needs to be between subjects, the second one needs to be within subjects, and our outcome variable needs to be continuous, meaning that it is measured on an interval or ratio measurement scale. So now let's shift gears and talk about the statistical assumptions that should be met prior to analyzing a mixed factorial ANOVA and definitely prior to interpreting the results. So the statistical assumptions that should be met for a mixed factorial ANOVA are as follows. First, for each population or cell, if you think about this as a contingency table where we have our two or more categorical predictor variables and then thinking of the different crosses or cells between them if we do a cross tabulation. So for each population or cell, the continuous outcome variable should have a univariate normal distribution. Second, the variances of the continuous outcome variable should be equal across all those different possible cells, if you think about it in terms of a cross tabulation. Now, the third and final assumption is that the difference score variances between levels of the within subject's predictor variable should be equal. Now, let's shift gears again and think about statistical significance in the context of a mixed factorial ANOVA. So we'll start with model level statistical significance. And so with a mixed factorial ANOVA, we will use an omnibus F-test and associated p-values. Now, this is not any different than any other type of ANOVA. We usually or typically would start by evaluating the model level statistical significance using some kind of omnibus F-test and its associated p-value. Now, with a mixed factorial ANOVA, we're going to use multiple F-tests and multiple p-values to test whether the means across levels of a between subjects predictor variable differ to a statistically significant extent, whether the means across levels of a within subjects predictor variable differ to a statistically significant extent, or whether the association between one predictor variable and the outcome variable depends on levels of the other predictor variable in the model. In other words, investigating whether or not there's evidence of a statistically significant interaction between two or more of our predictor variables. Now, for the sake of simplicity, I'm going to be focusing only on mixed factorial models that are two-way in nature, meaning we have just one between subjects factor and just one within subjects factor. So when we talk about statistical significance in the context of an omnibus F-test, we're going to be applying what's called null hypothesis significance testing. And this is where we interpret an associated p-value that goes along with that f-value. If it is less than 0.05 or whatever two or one-tailed alpha level that we set, if that p-value connected to that f-value is less than 0.05, then we are going to meet the standard for statistical significance, which means in null hypothesis significance testing that we would reject the null hypothesis that their means are equal or that the interaction is statistically significant. Now, if the p-value associated with the f-value is equal to or greater than 0.05 or whatever two or one-tailed alpha level we set, then we are going to fail to reject that null hypothesis that the means are equal or that the interaction is statistically significant. So when an interaction is statistically significant, and when I'm referring to an interaction, again, I'm saying that essentially the relationship between one predictor variable and our outcome variable is going to be contingent or dependent upon the second or third predictor variable that we have in our model. Now, when an interaction is statistically significant, we typically are going to follow up by testing for what are called simple effects or planned contrasts. So let's unpack each of those, starting with simple effects first. So with simple effects, for between subject variables, we can investigate whether there are differences across the means for each level of the within subjects variable. For within subjects variables, we can investigate whether there are differences across means for each level of the between subjects variable. Now, planned contrasts differ in that they're more targeted in nature. So, for example, for a between subject variable, we are going to investigate whether there are differences between specific pairs of means. And often these are ones that we're really planning for and we're targeting to compare. Okay? So again, for a between subjects variable, we can investigate whether there are differences between specific pairs of means within a given level of the within subjects variable. For within subjects variables, we can investigate whether the mean of the differences between two specific levels of our within subjects variable differ from 0 within a given level of our between subjects variable. Now, when an interaction is not statistically significant, we typically follow up by investigating only the main effects. And the main effects are specifically for a between subjects variable, we are going to investigate whether the overall means average across all levels of the within subjects variable differ significantly from each other. For a within subjects variable, we're going to investigate whether the overall means average across all levels of the between subjects variable differ significantly from each other. Now, when it comes to simple effects and planned contrast, and specifically statistical significance in the context of simple effects and planned contrast, we're also going to use null hypothesis significance testing, and it's going to have the same interpretation in terms of if a p-value is less than 0.05 or whatever alpha level we set, that is going to be our standard for statistical significance, meaning that we reject that null hypothesis, that the means or the mean of the differences is 0. Now, if the p-value is equal to or greater than 0.05 or whatever we set the alpha level to, then we're going to fail to reject the null hypothesis, and this is going to mean that the means are equal or that the means of the differences is equal to 0. Now, often the p-values, we're going to adjust them for what's called family-wise error when there are multiple simple effects or multiple planned comparisons that we're evaluating. Okay? And so this is to avoid capitalizing on chance by just doing multiple comparisons and running multiple sub or follow-up analyses. So now let's talk about an example of a mixed factorial ANOVA, and this is perhaps the most simple type of mixed factorial you can imagine, which is where we have, of course, one predictor variable that's within subjects and one predictor variable that's between subjects, but what's more is that there are only 2 levels for the between subjects variable and only 2 levels for the within subjects. So we have a 2x2 mixed factorial design. And so here's a classic example where this applies, which is when we have a pre-test, post-test with control group evaluation design. Okay, so this would be an example of potentially a quasi-experimental or a true experimental design. It would become true experimental design if we're also randomly assigning people to one of the conditions where one of those conditions is a control or comparison group. So as you can see here, we have everybody gets a pretest, and then they either take part in the training condition or the control condition, and then everybody gets a post-test. What's important to note here is that people either participate in the training program or the control program. They don't participate in both. So what does that mean? Well, that means that our training condition variable or condition variable is our between subjects variable, and it has 2 levels, a training level and a control level. Now, our pre-test and post-test variables, these are going to represent our within subjects test time variable, and again, they have 2 levels. Level 1, pre-test, level 2, post-test. Now, these are within subjects because every single person who goes through this evaluation, they're going to be assessed on the pre-test and they're going to be assessed on the post-test. So everybody's going to have scores on both of those. Whereas in contrast with the between subjects variable, the condition variable, people only have scores for one of those, or they're only exposed to one of those. So here's another way that you can think about this pre-test, post-test with control group design. So over here, we have a plot where on our x-axis we have time of assessment, so our pre-test and then our post-test, and our y-axis we have scores on those pre-test and post-tests. Now represented as a green triangle here is our training group, and the blue circle is our control group. If we were to only have a post-test and no pre-test, we would be able to determine whether or not there are statistically significant differences in scores after training on that post-test. However, what we wouldn't know is where people started. What was their level of whatever it is we're trying to measure before the training and the control conditions? And so that's where a pre-test and post-test with control group design comes into play. With a pre-test, we can figure out where people started. So for example, here you can see that really, if you imagine the training happening and the control happening somewhere in between the pre-test and the post-test, we see that these are essentially parallel lines, meaning that they improved at the same rate. and they did not start at the same place. So this would indicate that probably the training has very little, if anything, to do with increases in these scores. It's just that people in the training group happen to have higher levels of whatever it is we're trying to measure prior to training. Now, if we were to see something like this, this would imply an interaction. It would imply specifically a multiplicative interaction where we would see here that everybody starts at about the same place in terms of their pretest scores, regardless if they're going to be assigned to the training group or control group. But then after we see those differences on the post-test there. So this would be more convincing that we know where people started and that probably any differences that we observe post-training are likely due, at least in part, to the training itself. So I also want to point out at this point, since I just showed you an example of a 2x2 mixed factorial ANOVA where there are two predictor variables and each predictor variable has just two levels, in that specific context of a mixed factorial ANOVA, a mixed factorial ANOVA will be statistically equivalent to the following analyses. First, it's statistically equivalent to an independent samples t-test with a difference score outcome variable, where that difference score outcome variable is simply creating a difference score where for each person we subtract their post-test score minus their pre-test score, and that creates a difference score, and that's going to be our outcome variable in our independent samples t-test model. Our predictor variable is going to be the condition variable in this example. So it would be the variable that's categorical in terms of who is participating in the training program or the control condition. Now, a simple linear regression model with a difference score outcome variable is another statistically equivalent approach to analyzing these data. Now, with a simple linear regression with difference score outcome variable, it's going to be specified in much the same way as an independent samples t-test. Again, that difference score variable is going to be our outcome variable, and our categorical predictor variable is going to be the between subjects variable, which in the example I just showed you is that condition variable where there's training or control. We could also use a biserial correlation with that same difference score outcome variable, where here the difference score outcome variable would be our second variable, and our first variable would be that between subjects predictor variable. We could also estimate what's called a random coefficients model, which also is referred to as a linear mixed effects model, or in this specific context, a growth model. Now, due to the ease of implementation and interpretation, often we're probably going to opt for the simplest analysis, which in this case is an independent samples t-test with a difference score outcome variable. Now, I should note here that I'm talking about statistical equivalence when we have what's called a balanced design, which means that across the two conditions where we have the between subjects conditions, that we have the same sample sizes for example, those people who participated in the training program and those people who participated in the control program. Okay? So again, we have equal or approximately equal sample sizes, and that's what I mean when I say we have a balanced design in this specific context of a 2x2 mixed factorial ANOVA. So now let's shift gears again, and for the final time, so because we've talked about statistical significance, let's talk about effect size and practical significance now. Often when we find evidence of statistical significance, either at the model level of a mixed factorial ANOVA or at the simple effects, simple effects and or planned contrast level, we are going to then want to know, well, how big of an effect are we talking about that we found was statistically significant? And this is where we get into the realm of what often is referred to as practical significance. So effect size and practical significance can be considered at each stage of the mixed factorial ANOVA. And what I mean by that is we can talk about the effect size of our omnibus F-test. We can also talk about the effect size of simple effects or planned comparisons, as I mentioned a second ago. So what do I mean by an effect size? Well, here is a direct quote from the Task Force on Reporting of Research Methods in AERA publications from 2006. They described an effect size as, quote, an index of the quantitative relation between variables. Now, effect size that we're going to be focusing on, these are effect sizes that you can compare across models and across samples, meaning they have the same interpretation. And often we're going to apply qualitative interpretations to them, such as small, medium, large effects. So let's first start with those model level tests and those omnibus tests. And these are if we find a statistically significant F test as part of our omnibus test, then we're going to talk about effect size and practical significance in terms of eta squared or partial eta squared. So what's the difference between eta squared and partial eta squared? Well, simply put, eta squared is the proportion of variance explained by a predictor variable in our outcome variable in the model. Partial eta squared, on the other hand, is the proportion of variance explained by a predictor variable in the outcome variable when statistically controlling for other predictor variables and or interactions in the model. So down here at this table at the bottom, you can see some common thresholds or cutoffs that we typically associate with eta squared and partial eta squared. And they are, for something to be considered small, an effect to be considered small, it needs to be at least 0.01 or larger. But once it reaches 0.09, we'd often describe it as medium. And then once it reaches 0.25 or larger, we describe it as large. So lastly, let's talk about pairwise comparisons. So if we're comparing specific sets of means or specific pairs of means, for example, as part of follow-up tests or planned comparisons or simple effects, whatever the case might be, then we can choose to compute something like Cohen's d, which is the standardized mean difference, as that would allow us to compare the magnitude of the difference between each pair of means in terms of that standardized mean difference. Now with Cohen's d's, some common cutoffs that are often applied are the following, and those are small is going to be 0.2 or larger, medium is 0.5 or larger, and large is 0.8 or larger, okay? And I want to point out that the effect size cutoffs or thresholds or rules of thumb that I've mentioned thus far are just that. They're rules of thumb, meaning that they should be context specific. However, Cohen and some others have offered these very general thresholds or cutoffs to us, and they're very commonly applied for better or worse. So this wraps up the video on mixed factorial analysis of variance. We started with that overview of what mixed factorial ANOVA is and how it's distinguishable from other types of ANOVA, as well as distinguishable from common t-tests. We then talked about statistical assumptions that should be met prior to estimating a mixed factorial ANOVA model, and definitely before we interpret the findings or the results from a mixed factorial model. We then finished up with a discussion of statistical significance, effect size, and practical significance. We also talked about, too, the specific case of a 2x2 mixed factorial ANOVA, where when you have a balanced design, you have other options at your disposal in terms of analyses that are statistically equivalent, such as an independent samples t-test, a simple linear regression model, a biserial correlation, and a random coefficients model, which also is referred to as a growth model or linear mixed effects model. So this wraps up the video on mixed factorial analysis of variance.